Good evening, one and all gathered here. I would like to extend a warm welcome to all the participants for the second day of our online session of the Faculty Development Program. Now, it's my privilege to invite Dr. J. Kartiga ma'am, Professor, Department of Triple E, to introduce our honorable chief guest. We invite you to carry on, ma'am.
Good evening to all. I'm happy to introduce today's chief guest of the day, Dr. G. Mahalakshmi ma'am. Dr. G. Mahalakshmi Ganapati is a training team head in Power Projects. She completed her bachelor's degree in Madras University and postgraduate in Power Electronics and Drives from Anna University. Her research area for receiving a doctorate is the PMSM drives for EV applications and the high gain DC to DC converters designed to optimize renewable resources. She secured university rank at Anna University during her master's degree and is well known for her unique contribution to her research work. She has 15 years of experience that spans both industry and academia. Currently, she is heading the training department of the Power Project Unit Center in Chennai. Power Projects provide power system consulting services to power utilities and industries in Indian and global markets. We offer solutions and recommendations from small scale industrial systems to highly complex national grid level networks. Power projects established in the year 2006. We are committed to exceed the expectations of clients by providing cost effective, innovative solutions without compromising the quality of service that we offer. Our skills include every aspects of electrical engineering needs like power system studies, consultancy services, detailed engineering, design engineering, and technical support. She also focuses on the student community of engineering graduates from reputed institutions by organizing training programs and conducting vertical courses in power system and its basic design to enlighten the young minds of India. She is a ETAP and PSSC trainer with good exposure in power system studies and proficient in various simulation tools like ETAP 2020. Ma'am, we welcome you for this session, ma'am. Over to you, ma'am.
Thank you. Yes, thank you for the introduction, Dr. J. Kartiga ma'am. And
Thank you,
I
ma'am.
thank everyone who has invited me for this FDP. Thank you once again to one and all present here. Okay,
Ma'am,
so
shall I stop my screen, ma'am? Can you share your
yes,
PPT?
yes,
Yes,
I will.
thank you.
So good evening, all of you. It's a very special day for me because today I'm just addressing all the senior staff members of the college who are very proficient in already in power systems. And here I am just to add a few additional knowledge on your vast knowledge. Okay, you have already, I know you have vast knowledge on the power systems, but still, if my input is adding to that, I'll be very happy. Okay, so with that short note, I will share my screen. Whether my screen is visible, ma'am?
Yes, ma'am, it's visible.
Yes, yes, yes. Thank you so much for confirming. So today the topic I just saw in the poster, and it was really a great initiative. Why? Because we are only looking at the Indian grid. Okay, when we just look at the world, the topmost cities and all those there, it is equal to India. Okay, so today what I have done is I have just taken a study on Indian grid only. Okay, which will enhance our knowledge very, very, very well. And also in that you will see all the aspects of the power systems. So, am I audible?
Yes, ma'am.
Yeah, okay then. Okay, then I'll start. Okay. So before going to this PPT, I just wanted to say a few things about the power systems. So that is very basic. Okay. So what are the generations like? What are the generations we saw? We saw conventional, next we saw renewable, and we go for storage. So our main our main aim is the renewable energy storage solutions. So first is conventional. Conventional means those are the coal, thermal, and other nuclear, all those things are conventional. And what about the renewable? Renewable is the resources which are not going to be stopped, okay, which are not going to get over. Fossil fuels are getting over, but coal is getting over. But when we come for the renewable energy like wind and sun, biomass, these are all not going to get over by the years passing. When the years passing, they are not going to get over. So when we are going to meet these demands of India, then we have to mix all these renewable energy, conventional energy, and storage. And when we mix to meet these dynamic demand, what do you mean by dynamic demand? Dynamic demand is the ever changing load. The load is not constant. The ever changing load is dynamic demand. So we are mixing renewable energy, conventional, and storage to meet the dynamic demand. So that is what is going to be a big topic today. Okay, the today's topic is how we mix to meet the dynamic demand, and what we mix, and what are all the effects we face while mixing these generations. So generations, I mean renewable energy generation, conventional energy generation, and storage energy storage. That is the energy storage, BESS. You call it as battery energy storage, BESS. Okay, renewable energy storage. So both are coming under the same category. So previously in India, when we just see the grid was purely based on conventional, meaning there is no any renewable energy resources, and even if it is there, they are very, very insignificant. But now when we see the Indian total power generation and its capability, then you will really need more energy to think about it. So the first slide is India has made a significant strides in integrating renewable energy into its power systems. So as of December 2023, I'm going for back today. I'll just tell you later, but we'll just see what happened the last year. 2023, India's total installed electric capacity stands at approximately 400, keep it as 428 gigawatts. Gigawatts means it is 400 into 10 power 3 megawatts. Okay, here is the capacity which is generated by central, state, and private in megawatts. Okay, you add all those things, you get 420 gigawatts. And our peak demand during 2023 was 220 gigawatts. And the minimum demand was 80 gigawatts. Okay, so now you can see the range, how it is balanced. Okay, see the peak demand is 220 and minimum demand is 80. Now the power has to be, generation has to be balanced. Okay, so that is called as generation load balancing. Why we are focusing on that? Just to enhance the grid stability. And I have a lot of examples today to tell you how our Indian grid stability was in COVID 2020 and in 2024. Okay. And after that, in November 2024, India's highest installed renewable energy capacity reached 213.7 gigawatts. And you might be wondering, what is the total gigawatt? It's 428. And now within a short period, it is just reaching 40% of that. It is just going to reach 50. It is not cross 50. So it is nearly 40. So what are the renewable energy sources? We are focusing into 1.3. So 0.7 gigawatts is solar, wind, hydro, biomass, and small hydro power projects. Okay. So these are all the renewable energy. So the renewable energy capacity is 213.7 gigawatts as on November 2024. I have given the link here. Okay, you can also just click on the link to see these data, the current data. That is msn.com. So when including pipeline projects, the total non-fuel capacity surged to 472.9 gigawatts. And see that now non-fuel capacity itself is 472.9 gigawatts, which is unimaginable. And when we think in the future, how it is going to be, it's unpredictable. Okay, solar power leads the way with 94.7 gigawatts installed capacity, followed by wind power 47.96. See, there are lots and lots of job opportunities. Okay, nobody knows. They are simply thinking Tripoli does not have any job opportunities, but you should come out and see the Tripoli field. We are in lack of good engineers because everybody is going to software. We are in lack of good engineers. I just wanted to, since here a lot of college professors are here, I just wanted to say this sentence specifically. Please ask your students to focus on the core industry because the core industry is suffering due to less manpower. There are nobody in the design engineering part. Okay, we are just struggling to get good engineers. Even though they are from good institutions, they lack knowledge on power system basics. Okay, so I'm just doing the training. So I'm being a head of the training department. I'm training a lot of college students. Apart from college students, you might be wondering, I'm training the faculties in the GE, General Electric, and Nordex. All these are power systems company, consultants companies. The participants, the workers in there need training on power systems. So apart from this, so what is the main thing you could focus on is being a professor and assistant professors. Please ask your students to focus on ETAP and PSSC software, the simulation software, which will give them work from home job. Believe me, 50% of the engineers doesn't go to the office. They work from home. Only 3 days they go home. It is like a software only. So let at least now your students know about this ETAP training. Okay, this is what we are giving here and which is really, really valuable, and they can get a lot of jobs. Not only in ETAP, there are many software. If you want, you can make a note of it. It is ETAP, PSSC, PSCAT, Dixelant, PVSYST, that is a solar, which is blooming, and Homer Pro. All these are the software which gives you the training is only 1 month you need, and for the rest of the life you are going to work in a good great MNC, a corporate, which is going to give you a good salary equivalent to software just for a designing. Okay, designing and receiving the output and giving them the relevant data. Okay, so these are the things which I wanted to tell you. I just told you now. Please make a note of it. And next we can go to our topic. So the biomass. So the large hydro projects contribute 46.97 gigawatts and small hydro projects 5.08 gigawatts. This is nothing. We are going to take the water and store it in a height, and from there we get a hydroelectric power. Okay. Then biomass, waste to energy. So these are all playing a significant role in renewable energy mix. And when we just come to the various renewable energy sectors, various resources of renewable energy, we can see that solar, air, wind, water types, water flowing, soils, plants, all are the biomass. These are biomass, which is renewable. And here non-renewable, you can just see these are all the things: fossil fuels, oil, coal, natural gas are all renewables. Just a brush up, and these are all conventional. Sorry, these are all the renewable energy. Okay, so these are the renewables. That picture, it's in the picture form. Okay, so now we'll just go to the main part. Okay, so maintaining stability in India's power system involves several strategies. So first we'll see a few strategies, and from these strategies we'll see how we have managed a setback in India. Okay, that happened, a blackout in India, and how they overcome this. And also we are going to talk about the pan India light off moment in 2020 during the COVID. Okay, so here are some key approaches. So how we are going to ensure the reliability and efficient electric power supply. So first, balancing supply and demand. Okay, if we think balancing supply and demand is very easy, then mark my words, it's not going to be. Sitting in a dispatch center, you don't have control on the demand, but you have control only on the source generations. In as an engineer, when we sit in a dispatch center, that is a power dispatch center, we can just see where the demand is increasing, where the demand is shedding, that is the load shedding is happening, and where the supply need to cut. So you have to just adjust the generation. And if you don't have enough generation, then you should be going for load shedding. Okay, cut the power for the place where you have to curtail. Sometimes you have to curtail. Okay, you have to compromise. So what do we do is encouraging consumers to reduce or shift the electricity usage during peak times. See, this is really, if you think it's possible, then we could execute it. Okay, and next is energy storage system. Yes, energy storage system is what I'm going to talk about today, which is really going to add value to our knowledge. So utilizing batteries and other storage technologies to store excess energy and release it during high demand periods. This is possible. But how it is possible? Because it's a very expensive technology. Is it possible? But in near future, it is possible. I'll tell you how. Okay, because everybody going to buy a battery in future. If you don't believe me, just listen to this carefully. Okay, enhancing grid infrastructure, upgrading transmission distribution network. So we can do that. Modernizing and expanding the grid to reduce losses and improve reliability is possible. Smart grid technology, implementing advanced technology for better monitoring, control, and automation. Yes, we have monitoring, SCADA, all those things. And renewable energy integration. This is also very important. Because of this, I have some load disturbance and also some source disturbance. You should be thinking, if it is a solar is my supply, then how I'm going to rely on the impact. Okay, rely on impact. During an impact, how I'm going to rely on the additional expenses of load. Okay, if immediate demand of load is needed, then if it is solar renewable energy, then I have to adjust my power, or I have to add the power generation even before the frequency gets to 0.5 hertz below. How do I do that? With the help of battery energy storage system. Because when the solar is added, there is one drawback. What is the drawback? We don't get the kinetic energy out of the rotating elements. Okay, because solar is not rotating. I'll tell you how we get the kinetic energy. Okay, in this forthcoming hours. Okay, hydropower development. Expanding hydropower projects to provide a stable and renewable source of electricity. Yes, we can do that. And regulatory and policy measures. So incentives for renewable energy. Yes, we are now government is providing subsidies, incentives who are installing renewable energy in their house, in their factory, everywhere. In colleges, energy efficient programs, promoting energy efficiency measures in industries, buildings, appliances is possible because they are not going to pay penalty. If they don't want to pay penalty, they have to just promote energy efficiency measures. Okay, load shedding. So intelligent load shedding is what we have to concentrate on. Instead of load shedding, we have to concentrate on intelligent load shedding. That is curtailing. Okay, curtailing the loads which are not going to operate. Okay, which need not operate continuously. Black start capability. So without external power supply, can we ensure the power plants to start? Let's see. Okay. So in interstate power exchange, so this has been done by the national grid for a long period. Participation in regional power pools, collaborating with neighboring countries. Yes, these are all the things which we can do to improve our grid stability. By implementing these strategies, India can maintain stability in its power system and meeting the growing electricity demand efficiency. So we now saw all the methods for maintaining the grid stability. So now how do we maintain the grid stability? Okay, how we maintain the grid stability? So apart from this, when we just wanted to know about our power systems, we should know about the 5 states of power systems. This many of you would have seen in the Prabha Kuntur book. Okay, I'm not going to talk much about it. I'm just going to give you a small introduction about it. So in this, the main aspect we are going to see is the equality and inequality constraints. So before going into that, just let's see one glance about what is normal, alert, emergency, and restorative and in extremes. So there are several states describe the operating conditions and behavioral systems. These states help in analyzing, managing the performance, stability, and reliability of the power grid. So the first is the normal state. Normal state is where the equality constraint and inequality constraints are satisfied. So as of now, what do you mean by equality and inequality constraints? Anyone can tell me, or can I get any answer in the chat? What is equality and inequality constraints? Yes? Okay, so let me tell. Equality constraints. There are 2 sets of equality constraints. The total power generated must be equal to the total load demand plus losses. The power system, that is most dynamic in the world, where generation and consumption happen simultaneously. What do you mean by that generation and consumption happen simultaneously? See, when you are switching on a washing machine at your home, there is someone who has switched off their fridge at the same time. So thereby the generation and the demand is balancing. The generation and demand is balancing because someone has switched off their appliances simultaneously when you are switching on your washing machine, or when you are switching on your any other device like motor, fan, any AC, someone has switched off their device. If that is not happening, because at evening 6 o'clock in the summer days when you switch on the AC is not running. Do you know why? Because there is demand is not met. The generation, the demand is not. Nobody is going to switch off because you are going to switch on the AC in the evening 6 o'clock, because they also need it. Okay, they also need it. They can't switch off the light because they don't want to work in without light. They don't want to read without light. So you also switch on, they also switch on. So at that time, we are in a position to maintain the equality. So this is called as equality constraints. So in that case, we have 2 equalities. What did I tell you? The load, the generated real power, reactive power should be equal to the demand, real and reactive demand, and also the set voltage should be equal to the sending end voltage should be equal to the receiving end voltage. So that is the other equality constraint. So I told you as of now 2 equality constraints. For example, I'll just give you one example. For a small grid, if the total load is 500 megawatt and the losses are 20 megawatt, what should be the total generation? Any answers? The total generation should be 500 load plus 20 losses. It should be 520 megawatt. If I'm not wrong, It is 520 megawatt. And similarly, the other voltage constraint. If the voltage at any bus should be maintained at 230 kV, this needs to be ensured across the system. So the whole system under the bus should be maintained at 230. If is it not so, if that is not happening, then the equipment are going to work in under voltage condition, and which is going to spoil the equipment or it is going to reduce the life of the equipment. Okay, so that is going to happen. So now in inequality constraints, always remember two things you have to look into it. One is the generated, the total power generated must be equal to the load demand plus losses, and the voltage at specific bus should be maintained at certain levels. So these two are very important. So now when we just see this, what is that inequality constraint? So there are some parameters which has to be maintained lesser than the prescribed value. What is that? For example, if I have a transformer, the transformer rating is 1000 MVA. Can I load it for full 1000 MVA rating? I should not do it. Usually in industries, to maintain the contingency analysis, I'll tell you what is contingency later. To maintain a contingency, what they do is they usually load a transformer only to 50% of it. And if it is a distribution transformer at your street, just ask the EB station how much it is loaded. They would have told you when it is installed, it was loaded only to 50%. After, when many houses are emerging, then it adds and it went up to 80, but they will never load it up to 100, because when there is any emergency situation, this transformer might be overloaded, so that they will not allow. Okay, that will lead to a critical situation. And also if the transformer is fully overloaded for 100% and it is continuously running for 24/7, then it is going to get overheated and someday it is going to show its true colors. Okay, so now the transformer is not being overloaded. So what's the limit there is the rating. Okay, so the first inequality constraint is power flow on a transmission line. It might be a transformer or a transmission line must not exceed their thermal limits. So why did I tell you? Why did I tell you that transformer should be limited only up to 80% of it? Because 80% of it, if it is exceeding 80% and it is running continuously for a long hours, then it is certainly going to get heated. So what is the one limit which I'm relying on? It's a thermal limit. So the power flow on transmission line must not exceed the thermal limit, or loading of any equipment should be within its rating. This is what I meant as inequality constraints. So in that inequality constraints, we have to maintain the total apparent power or the real power or reactive power, whatever it might be. Transformer is rated in MVA. Okay, that is apparent power. So whatever the supply or whatever the rating of the transformer, the load should be lesser than that. So P rating or S rating should be less than or equal to the flow. Okay, flow of the power flow. Okay, so if it is a 25 MVA transformer, you will be limiting it with 20 MVA load. Okay, then next is generator power output. Okay, so the next inequality is generator output limits. So each generator output must be within its operating range. So I have already told you that rating is very important. So in generation, the most stringent constraint available for any equipment, if we see in this power system, that is generator. Okay, even a transformer, you can load it to its fullest for a few hours. Even though if it is, you can load above it. Okay, you can load 110% or 120%. The transformer you can load it, but not for all the 24 hours, but you can load it for 1 or 2 hours. Okay, because once you remove the loads, the transformer is going to come to its normal, but it can just operate for 110%. But this generator, it will be operating only within its limit. If it is a 900 megawatt generator, the maximum real power you can extract from is it only 800. Okay, there is a limit. And if it starts from zero real power factor, you cannot go to a minimum zero real power. Okay, if it you can the minimum real power you can extract is limited. Okay, if it is a 900 megawatt generator, the minimum you should extract from it is 500 or 400. That is the limit. Okay, so the generator has most stringent constraint. Why? Because the generator has its own inertia. It has turbine. The steam has to be in one pressure, and if it goes below that pressure, the turbine won't rotate. If the nozzle, if you just keep on decreasing, then the real power generator will be reduced. But to an extent, if you reduce the nozzle steam output, which hits the turbine and moves the rotor, it won't move when it is not overcoming its inertia, mass inertia. So there, the generator goes off. Okay, so you should always maintain a minimum power that can be extracted from the generator. So the generator is what? The most having the most stringent constraints. And also it under you might be thinking I can make it to work over excited mode, but there is a